question. When the restoring force is directly proportional to the displacement from equilibrium, the resulting motion is called simple harmonic motion. An ideal spring obeys Hooke's law, so the restoring force is Fx is equal to minus Kx, which results in simple harmonic motion. Simple harmonic motion is the projection of uniform circular motion onto a diameter, as illustrated below.
Characteristics of simple harmonic motion.
For a body vibrating by an ideal spring, omega is equal to 2 pi under root m upon k. Follow example 14.2 and figure 14.8 below. Figure A, find force constant k of the spring. And figure B, find frequency, angular frequency, and period of oscillation.
Displacement as a function of simple harmonic motion.
Given below is the formula for the displacement is a function of time for SHM with phase angle phi, and x versus t graph showing the changes in the values of m, a, or k.
Displacement, velocity and acceleration.
The displacement is a function of time for SHM with phase angle phi is minus omega a sine omega t plus phi. As always, velocity is the time derivative of displacement. Likewise, acceleration is the time derivative of velocity or the second derivative of displacement.
Now, given below are the graphs of displacement, velocity, and acceleration. You can have a look at them. Energy in simple harmonic motion.
Total mechanical energy, E, is equal to K plus U, which is conserved in SHM. E equals to half into Ka square, which is a constant.
Now, given below is the energy diagram for simple harmonic motion. You can have a look at them. Energy and momentum in simple harmonic motion.
Let us consider an example where a block of mass m, attached to a horizontal spring with force constant k, is moving in SHM with amplitude a1. Now, as the block passes through its equilibrium position, a lump of putty of mass m is dropped from a small height and sticks to it. Find the new amplitude and period of the motion. Repeat the above part if the putty is dropped onto the block when it is at one end of its path.
Now we are going to talk about simple pendulum.
Other systems can show SHM. Consider a simple pendulum that consists of a point mass suspended by a massless, unstretchable string. If the pendulum swings with a small amplitude, θ, with the vertical, its motion is simple harmonic, where the restoring force is the component of gravity, along the arc of the motion.
Damped oscillations.
Real-world systems have some dissipative forces that decrease the amplitude. Such dissipative forces are typically proportional to the speed v and appear in the force equation with minus sign. The decrease in amplitude is called damping, and the motion is called damped oscillation. The mechanical energy of a damped oscillator decreases continuously. For a periodic wave, each particle of the medium undergoes periodic motion. The speed of the wave is not the same as the speed of the particles. The wavelength lambda of a periodic wave is the length of one complete wave pattern. The speed of any periodic wave of frequency f is v equals lambda f. Example 15.1. The speed of sound in air at 20 degrees Celsius is 344 meters s. What is the wavelength of a sound wave in air at 20 degrees Celsius if the frequency is 262 Hz?
Periodic longitudinal waves.
The restoring force, that is, pressure, is in the same direction as the wave propagation. You may have a look at the given figures.
Periodic transverse waves.
This difference in direction of the waves and particles is why the wave is called a transverse wave. Note that the restoring force is transverse to the direction of the wave propagation.
The speed of a wave on a string.
When a portion of a string under tension is displaced, a wave will be launched along the string. The text gives two explanations of how to derive the velocity of the wave, but I find both to be relatively tedious and uninspiring. It is probably not surprising that the velocity will depend on the tension force, F, and on the weight of the string. Think of a guitar whose strings are all at the same tension. The thicker strings will produce a lower tone due to the slower speed of the wave.